Okay, let's just jump right in. We're going to talk about one of the most important and, yeah, one of the most difficult equations in all of physics. Think of it like a master code for, well, everything that flows. The weather, the blood in your veins, you name it. But here's the kicker. For all its power, it's considered pretty much unsolvable.
And here it is, the Navier-Stokes equation. I know, it looks a little intimidating, right? But what it does is actually kind of beautiful. At its heart, it's just Newton's second law, F equals ma. But for fluids, it's this single set of rules that, in theory, governs almost everything that flows. We're talking about the air over a plane's wing, water rushing down a river, even the magma churning inside the earth. This one equation is supposed to describe all of it.
Okay, so if we have this master equation, what's the big deal? Why is it so notoriously hard to actually use? Well, it all comes down to one little problem. It's nonlinear. You see those terms in there? They mean that the fluid's own motion feeds back on itself, which can create all sorts of chaotic, wildly unpredictable behavior. Finding a general, exact solution is so difficult that, get this, it's one of the 7 Millennium Prize problems. Yep, there's a $1 million prize waiting for anyone who can crack it.
So that difficulty basically forces you down one of two paths. Path 1, the exact path, is trying to solve the whole monster head-on. And that's, well, it's pretty much impossible for most real-world scenarios. But then there's path 2, the approximate path. This is the engineer's secret weapon. Instead of wrestling with the full equation, we get clever and simplify it. And this has given us this incredible toolkit of approximations, each one perfectly tailored for a specific type of flow.
All right, so let's check out our first approximation. To do that, we're going to visit a pretty extreme world, a place with what's called a low Reynolds number. Now, this is the world of the very, very small and the very, very slow. It's a place where a force we completely take for granted in our daily lives, inertia, just disappears.
Think about it. When we swim, we use inertia, right? We push off the wall of a pool and our momentum carries us forward. We glide. But for something like a bacterium, the world is totally different. For that little guy, water feels as thick and sticky as honey. There's no such thing as gliding. The very second it stops wiggling its little tail, it stops. Just dead in the water. Motion for it is just this constant, exhausting struggle against the fluid's stickiness, its viscosity.
So, welcome to the world of creeping flow. This is what happens when that Reynolds number, which is really just a way to compare inertia forces to sticky, viscous forces, is super, super small. And in this world, we can do something amazing to the Navier-Stokes equation. We can simplify it a lot. The entire left side of the equation, the part that represents inertia, it just goes away. Poof. All you're left with is a really simple balance, pressure pushing the fluid and viscosity resisting it.
And getting rid of inertia has a really, really bizarre side effect. In this creeping flow world, density, a property we think of as totally fundamental, it just vanishes from the equation. It's not there anymore. It's like a fluid particle in this world literally has no concept of what density even is. Drag has nothing to do with how heavy something is, it's purely about how sticky the fluid is.
Here's a great way to picture this. Imagine a kid trying to swim through a giant ball pit. The only way they can move is by constantly thrashing around. The second they stop moving, they are just stuck. There's no gliding, no coasting forward. That is a perfect analogy for what life is like for a bacterium in this low Reynolds number world.
Okay, so now let's do a complete 180. We're going to jump to the total opposite extreme, the world of ideal or perfect flow. We're leaving that slow, sticky realm behind and heading to a high Reynolds number world. Here, inertia is king, and we're going to pretend we have a perfect fluid with absolutely zero friction.
So in these so-called inviscid regions, we make a pretty bold assumption. We just say, you know what, let's pretend viscosity is zero. When we do that, the big, scary Navier-Stokes equation simplifies way down into a much friendlier version called the Euler equation. Now, of course, no real fluid is truly perfect. But for big, fast-moving flows, think about the air way out far from an airplane. Those sticky forces are just so tiny compared to the inertial forces that we can pretty much ignore them without getting into too much trouble.
And this simplified model turns out to be incredibly useful. It can be used, for example, to model the flow inside a tornado. The Euler equation perfectly predicts that as the air starts spiraling faster and faster and faster towards the center, the pressure just plummets. And that massive pressure difference between the core of the tornado and the air outside, well, that's exactly what makes them so terrifyingly destructive. But there's a catch. This idealized theory has a major blind spot. It works great for these big, open flows, but what happens when our perfect, frictionless fluid runs into a solid object? Well, that's where the whole theory leads to a really famous paradox and just completely falls apart.
And this is known as D'Alembert's paradox. The math, the beautiful, elegant math of this ideal flow, predicts that the total drag force on any object moving through it should be zero. Nothing. The theory says the pressure on the front of an object is perfectly canceled out by the pressure on the back. But we all know that's just wrong. I mean, stick your hand out of a moving car window, you feel drag, right? This was a huge puzzle for scientists back in the 18th century. It basically created a crisis in fluid dynamics.
So how on earth did they solve this thing? The big breakthrough didn't come until 1904 from a German engineer named Ludwig Prandtl. He's the one who found the secret ingredient, the idea that finally bridged these two very different worlds. And that secret was the boundary layer.
See, Prandtl's genius was realizing that the ideal theory was almost right. The problem wasn't with the flow way out in the open. The problem was in a tiny, razor-thin layer of fluid right at the surface of the object. In that little layer, a super important rule called the no-slip condition takes over. It just means that the fluid touching a surface has to stick to it. It has to have zero velocity. And inside that thin layer, suddenly viscosity isn't zero. In fact, it's everything.
So Prandtl's brilliant idea was to split the problem in two. He said, look, far away from the object, let's just use the simple Euler equation. That's the outer flow. But right up close to the object, we have to deal with this thin boundary layer where viscosity is a huge deal, where it's slowing the fluid down from full speed all the way to a dead stop right at the wall. And this discovery has a really dramatic consequence. Remember that ideal theory? It predicts a perfectly smooth, symmetrical flow over something like a bump. But in the real world, that slow-moving fluid inside the boundary layer, it just doesn't have enough oomph, enough momentum to push through the increasing pressure on the back side of the bump. So what does it do? It gives up. It actually detaches from the surface. And we call this flow separation.
And that separation is the key. It creates this big, messy, turbulent region of low pressure behind the object, what we call a wake. And all of a sudden, that high pressure pushing on the front of the object is no longer balanced by pressure on the back. This massive pressure imbalance creates a powerful pull backwards. And that, my friends, is pressure drag. It's the missing piece of the puzzle that finally solves D'Alembert's paradox.
Okay, so let's recap. We've got these three different worlds, right? We have the super sticky creeping flow, the perfect and frictionless Inviscid flow, and then the boundary layer, which is the bridge that connects them. So the big question is, how do engineers actually use this amazing toolkit to design real things in our world? Well, it all comes down to a pretty straightforward workflow. First, you look at the problem and you calculate the Reynolds number. That tells you which forces are in charge, inertia or viscosity. Then, based on that, you choose the right tool for the job, the right simplified world. You go ahead and solve that much easier problem. And then, and this is important, you double-check that your first assumption was actually a good one. You see, the real art of fluid dynamics isn't about brute forcing the full equation. It's about having the wisdom to know which shortcut to take and when.
And now we can use this knowledge to do some really amazing things. Here's a fun fact that sounds totally backwards at first. A messy, chaotic, turbulent boundary layer is actually stronger than a nice, smooth laminar one. Because it's all mixed up, it's fuller, it carries more energy and momentum closer to the wall. And that extra energy makes it way more resistant to that flow separation we just talked about.
And this, right here, is the secret behind a golf ball's dimples. It's pure genius. If a golf ball were smooth, the boundary layer would be smooth and laminar, and it would separate from the ball really early. That would create a huge wake behind it and a ton of drag. But the dimples act like little tripwires. They deliberately mess up the flow, forcing that smooth boundary layer to become turbulent, and that energized, turbulent layer can now hug the surface of the ball for way longer before it finally separates.
The result? A much smaller wake and dramatically less drag. It's the reason a dimpled ball flies so much farther than a smooth one.
So there you have it. That's the engineer's toolkit. Instead of one giant, unsolvable equation, we have these three incredibly powerful approximations. We've got creeping flow for the tiny, microscopic world. We have inviscid flow to look at the big picture. And we have the boundary layer, the crucial link that connects our perfect theories to messy, everyday reality. Each tool is designed to solve a specific piece of the grand puzzle.
And really, this ability to simplify, to know which details are critical and which ones you can safely ignore, that's the whole key. It's how we design faster cars and more efficient airplanes, how we understand the way blood flows through our bodies, or how a tiny bacterium swims. These powerful approximations are the secret. They're what let us see the world through the eyes of a fluid dynamicist, and they're how we turn a supposedly unsolvable problem into an incredibly practical and powerful tool.